This one is problem 3.12. Here we have a cantilever beam on which there is a point load right here, and there is a distributed load which is W0 right here. So in terms of support reactions, we'll get a support in y direction and a moment reaction right here. In terms of cuts, we need one cut right here, so let's call this cut 1, and another cut right here, let's call this cut number 2. So for analysis, let's draw the free body diagram for cut number 1. So cut number 1 is going to have this force P acting downwards. Your cut is always made at a distance of x, so this is going to be x right here. Now since this is a positive phase, we are going to get a shear force acting upwards and a bending moment counterclockwise. If you write the force balance equation for this, we get your V1 equals to P straightforward, and your MB1, which is going to be minus P times x, because MB1 is going to be anticlockwise and Px is also going to be anticlockwise, that's why minus Px. These are the values in your segment 1 of the beam. Now let's go for your cut 2. Now in cut 2, although this part is easier for us to analyze, but since we do not know these reaction forces, let's go and analyze the left part of this beam. So this is again force P here, and only some part of this UDL will come into picture, and again your distance for this cut is x from here to here. Since this one is L by 2, this part where your UDL is acting is going to be x minus L over 2. Now positive phase again, so we are going to have your shear force V2 and MV2 acting in this manner. Now for analysis, we can substitute this UDL with a point load. So we always substitute a UDL with a point load right at the center, and the net force at that point is going to be W0 times this distance on which it is acting. So x minus L by 2, and these distances, these are going to be exactly same. So it's going to be x minus L by 2 divided by 2, one of these distances right here. So again we do the force balance for this. So in force balance we have total 3 forces here. So P is acting downwards, so minus P. This force is also acting downwards, so minus W0 x minus L over 2, and plus V2, which is acting upwards, equals to 0. So this gives us the value of V2, which is equals to P plus W0 x minus L divided by 2. So this is the shear force in the second segment. Now if we do moment balance, we'll do about this point right here. Your MB2 is counterclockwise, so your P will also give you counterclockwise, sitting at a distance x from there, and your W0 x minus L by 2, this is also counterclockwise, so plus W0 x minus L over 2, that's the force, times this distance from here to here, which is again x minus L by 2 divided by 2 equals to 0. So from this you can see your MB2 value is minus Px minus W0 and divide by 2 x minus L over 2 whole square. So that's the value of your bending moment in the second segment. So now let's draw an axis to draw these shear force and bending moments. So I've drawn this axis here. This is where your cut 1, so V1 and MB1 will be plotted here, and V2 and MB2 will be plotted in this region. So let's focus on V1. The value of V1 is P, so we are going to have a constant value in this region, which is a positive P value, and your V2 value is right here. So this is an equation for line. We need 2 points to plot this equation. One point is going to be at x equals to L by 2, and another point is going to be at x equals to L, which is right here. So if I evaluate this at x equals to L by 2, the second term will become 0 here. So the only thing that we are going to get is P. So we are going to match this value right here. Now if I go to x equals to L, we get this P, plus from this side we are going to get W0 L by 2. So we are going to increase this value y. So this is your P. So we are going to further add this, which is W0 L by 2 from here to here. So this is your shear force. The convention that we are following is this right here, and we can shade this region. So this is how your shear force diagram for this beam looks. Now coming to the bending moment, we have to plot MB1 first. So this is again a straight line. We need 2 points for this. We can evaluate this at x equals to 0, which is right here, and x equals to L by 2. So at 0, this is going to give us a value which is 0. So we start here. At x equals to L by 2, this will give minus P L by 2. So we can draw it here, and we can connect them by a straight line. So this is how your bending moment is in segment 1, and this value right here is minus PL divided by 2. Now if you look at your second segment here, this is a parabola. For parabola we need 2 points and the peak. So 2 points in this case are going to be this value at x equals to L by 2 and L. If I check at L by 2, the second term is going to be 0, and this first term is going to give you minus PL by 2. So we have to start at the same point, which is right here. Now for the second term, we are going to get minus PL from here, and that value PL is nothing but, if I take this line and continue like this, this is the value which is minus PL right here. But to this value we are going to add this term also, which will give you minus W naught over 2 L by 2 whole square, right? So we are going to further drop this value by this distance, which is W naught by 2 L by 2 whole square, right? Since in the negative directions, it's going to drop there. Now at this point, if you notice your shear force coming from this side and coming from this side, it's matching there. So the slope of this curve, which is your MB1, and slope of MB2 should match. So even though this is a parabola which is opening downwards because this coefficient is negative for x square here, the slope at this point is going to be exactly same. So you're going to follow this slope right here, and then you're going to further drop in this sense. So that's how your parabola is going to be in this region. Now if you look at the peak for this parabola will be somewhere on the left side of this L by 2. So your peak is going to be somewhere here, and that will depend on the value of P naught and W naught. And if you want to understand where this peak is going to be, you can take the value of V2 and put that equals to 0. From that you'll get the value of x, and that is going to correspond to your peak location. So if I shade this region here, this is how your bending moment diagram is. So your maximum moment is happening at this point right here, which is a combination of these two, minus PL minus W naught by 2L by 2 whole square. And your maximum shear force is also happening at this point, which is P plus this value right here.